Today we're diving into the fascinating world of Coulomb's law, a fundamental principle in physics that describes the force between two electric charges. Whether you're a student, a science enthusiast, or just curious about how the universe works, understanding Coulomb's law is essential. This law not only explains how charged particles interact, but also lays the groundwork for much of modern physics and engineering. So let's embark on this journey together and unravel the mysteries of electric forces, starting with the basics of what Coulomb's law is and why it matters. Before we get into the law itself, let's meet the man behind the name, Charles Augustin de Coulomb. He was a French physicist born in the 18th century, renowned for his pioneering work in electrostatics and magnetism. Coulomb's meticulous experiments and mathematical approach led to the formulation of the law that now bears his name. His contributions have had a lasting impact, influencing countless discoveries and innovations in science and technology. Understanding his background helps us appreciate the significance of his work and the context in which Coulomb's law was developed. Coulomb's law didn't just appear overnight. It was the result of careful experimentation and observation. Using a torsion balance, Coulomb measured the forces between charged objects and noticed a clear mathematical relationship. His findings were published in the late 1700s and quickly became a cornerstone of classical physics. The law provided a quantitative way to predict how electric charges interact, which was revolutionary at the time. This breakthrough paved the way for future research in electricity and magnetism, setting the stage for the development of electromagnetism as a whole. At its core, Coulomb's law describes the force between two-point charges. It states that the magnitude of the electrostatic force between two stationary charges is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This means that as charges get larger, the force increases, but as they move further apart, the force decreases rapidly. This simple yet powerful relationship is fundamental to understanding how charged particles behave in everything from atoms to large-scale electrical systems. Let's look at the mathematical expression of Coulomb's law. The formula is F equals K Q2/R2. Here F represents the electrostatic force between the charges, Q1 and Q2 are the magnitudes of the two charges, R is the distance between their centers, and K is Coulomb's constant. This equation allows us to calculate the exact force between any two-point charges, making it a powerful tool in physics. Understanding each component of this formula is key to applying Coulomb's law in real-world scenarios. Let's break down the variables in the formula. The charges Q1 and Q2 can be positive or negative, representing protons and electrons, for example. The distance R is always measured from the center of one charge to the center of the other. Coulomb's constant K is a fixed value that makes the units work out correctly. By plugging in different values for these variables, you can see how the force changes depending on the situation. This flexibility makes Coulomb's law applicable to a wide range of problems in physics and engineering. Coulomb's constant, often denoted as K, is a crucial part of the law. Its value is approximately 8.99 x 10⁹ m2/c2. This constant ensures that the units in the formula are consistent and allows us to calculate the force in newtons. The value of K is derived from the properties of the vacuum and the fundamental constants of nature. Understanding this constant helps us appreciate the precision and universality of Coulomb's law, as it applies everywhere in the universe, not just on Earth. Coulomb's law not only tells us the magnitude of the force but also its direction. Like charges repel each other while opposite charges attract. This means that two positive charges will push away from each other, while a positive and a negative charge will pull towards each other. The direction of the force is always along the line connecting the two charges. This principle is fundamental to understanding the behavior of electric fields and the structure of atoms and molecules. To better understand Coulomb's law, it helps to visualize the forces at play. Imagine two charged spheres suspended in space. If both are positively charged, you'll see them move apart as they repel each other. If one is positive and the other negative, they'll move together attracted by the force. These visualizations make the abstract concept of electric force more concrete and relatable, helping us grasp how charges interact in the real world. Coulomb's law is most accurate when applied to point charges, objects so small that their size can be ignored compared to the distance between them. In reality, most charged objects have some size, but as long as the distance between them is much greater than their dimensions, the law still gives a good approximation. This concept is especially useful in atomic and molecular physics, where electrons and protons can be treated as point charges for calculation. It's important to remember that force is a vector quantity, meaning it has both magnitude and direction. When dealing with multiple charges, you need to consider the direction of each force and use vector addition to find the net force. This can make calculations more complex, but it's essential for accurately predicting the behavior of systems with more than two charges. Understanding vectors is a key skill in physics and engineering, especially when applying Coulomb's law. More than two charges are present, the superposition principle comes into play. This principle states that the total force on a charge is the vector sum of the forces exerted by all other charges individually. In other words, you calculate the force from each charge separately and then add them together, taking direction into account. This approach allows us to analyze complex systems with multiple interacting charges, making Coulomb's law a versatile tool in physics. Coulomb's law, the standard unit of charge, is the Coulomb C, named after Charles Augustin de Coulomb himself. The force is measured in newtons N. 1 coulomb is a large amount of charge, so in practice we often deal with microcoulombs or nanocoulombs. Understanding these units is crucial for performing calculations and interpreting results correctly. The use of standardized units ensures consistency in scientific communication and experimentation. Let's walk through a simple example. Suppose you have two charges, one is 2 microcoulombs and the other is 3 microcoulombs, separated by a distance of 0.5 meters. Using Coulomb's law, you can plug these values into the formula to find the force between them. This step-by-step calculation helps solidify your understanding of how the law works in practice and demonstrates its practical utility in solving real-world problems. Coulomb's law plays a vital role in understanding atomic structure. The attraction between negatively charged electrons and positively charged protons in the nucleus is governed by this law. It explains why electrons remain bound to atoms and how chemical bonds form. Without Coulomb's law, the structure of matter as we know it would be impossible. This fundamental force shapes the behavior of atoms, molecules, and ultimately all matter in the universe. Beyond physics, Coulomb's law is essential in chemistry. It helps explain how atoms bond to form molecules, the strength of ionic bonds, and the behavior of ions in solutions. The law provides a quantitative basis for understanding chemical reactions and the properties of materials. By applying Coulomb's law, chemists can predict the stability of compounds and the outcomes of reactions, making it a foundational concept in the field. Engineers use Coulomb's law in a variety of applications, from designing electrical circuits to developing new materials. The law helps in calculating the forces between charged components, ensuring the safety and efficiency of electronic devices. It's also used in fields like telecommunications, where understanding the interaction between charges is crucial for signal transmission and reception. Coulomb's law is truly a cornerstone of modern engineering. While Coulomb's law is powerful, it does have limitations. It applies best to point charges in a vacuum and doesn't account for the effects of other materials or relativistic speeds. In real-world situations, factors like the presence of other charges, the medium between charges, and high velocities can affect the force. Understanding these limitations is important for knowing when and how to apply the law accurately. Force calculated by Coulomb's law assumes the charges are in a vacuum. However, if there's another material between the charges like air or water, the force is reduced. This is because different materials have different permittivities, which affect how electric fields propagate. Engineers and scientists must take this into account when designing systems that rely on electrostatic forces, ensuring accurate predictions and safe operation. Relative permittivity, also known as the dielectric constant, measures how much a material reduces the electric force between charges compared to a vacuum. Materials with high permittivity, like water, significantly weaken the force. This concept is crucial in designing capacitors and other electronic components, where controlling the strength of electric forces is essential for proper function. You might be surprised to learn that Coulomb's law affects many aspects of daily life. From the static electricity that makes your hair stand on end to the operation of electronic devices, the forces between charges are at work all around us. Understanding this law helps us appreciate the invisible interactions that shape our world, from the smallest particles to the largest machines. Static electricity is a common example of Coulomb's law in action. When you rub a balloon on your hair, electrons are transferred, creating a charge imbalance. The resulting attraction or repulsion between objects is governed by Coulomb's law. This simple phenomenon demonstrates the power of electric forces and provides a tangible way to observe the law in everyday situations. Lightning is another dramatic example of Coulomb's law at work. During a thunderstorm, charges build up in clouds and on the ground. When the force between these charges becomes strong enough, it overcomes the resistance of the air, resulting in a lightning strike. This powerful display of nature is a direct consequence of the forces described by Coulomb's law. Coulomb's law is closely related to the concept of electric fields. An electric field is a region around a charged object where other charges experience a force. The strength and direction of this field can be calculated using Coulomb's law, providing a deeper understanding of how charges influence their surroundings. Electric fields are fundamental to many technologies, from capacitors to particle accelerators. Visualizing electric fields can help make the concept more intuitive. Field lines are used to represent the direction and strength of the field around a charge. The closer the lines, the stronger the field. These visual tools make it easier to predict how charges will interact and how forces will be distributed in different situations. Coulomb's law is often compared to Newton's law of universal gravitation. Both laws describe forces that act at a distance and have similar mathematical forms with an inverse square relationship. However, while gravity always attracts, electric forces can attract or repel. This key difference leads to a wide variety of phenomena in the electric world, making Coulomb's law unique and versatile. Both Coulomb's law and the law of gravitation follow the inverse square law, meaning the force decreases with the square of the distance between objects. This relationship is fundamental in physics and explains why forces become much weaker as objects move apart. Recognizing this pattern helps us understand a wide range of physical phenomena, from planetary motion to atomic interactions. The discovery of Coulomb's law marked a turning point in the history of science. It provided a mathematical framework for understanding electric forces, paving the way for the development of electromagnetism. The law's influence can be seen in the work of later scientists like Faraday and Maxwell, whose theories built upon Coulomb's foundation to create the modern field of electromagnetism. Today, Coulomb's law remains a fundamental principle in physics. It's used in research ranging from particle physics to astrophysics, helping scientists understand the forces that govern the universe. Advances in technology have made it possible to test the law with incredible precision, confirming its accuracy and relevance in a wide range of contexts. While Coulomb's law is a classical law, it still plays a role in quantum mechanics. The interactions between charged particles at the quantum level are influenced by the same principles, though quantum effects add complexity. Understanding how Coulomb's law fits into the broader framework of quantum physics helps bridge the gap between classical and modern science. Particle accelerators rely on Coulomb's law to control and manipulate charged particles. By applying electric fields, scientists can accelerate particles to high speeds and study their interactions. This technology has led to major discoveries in physics, including the identification of new particles and the exploration of fundamental forces. Coulomb's law also has applications in medicine. Techniques like electrostatic precipitation are used to remove particles from the air in hospitals, improving air quality. Medical imaging technologies and treatments for certain conditions also rely on the principles of electric forces, demonstrating the law's broad impact beyond traditional physics. In the field of nanotechnology, Coulomb's law is essential for understanding the behavior of tiny particles and molecules. The forces between charges at the nanoscale can determine the properties and functions of new materials. By mastering these interactions, scientists are developing innovative technologies with applications in electronics, medicine, and materials science. Electrostatic precipitators use Coulomb's law to remove particles from gases in industrial processes. By charging particles and then attracting them to oppositely charged plates, these devices help reduce air pollution and improve environmental quality. This practical application shows how fundamental physics can lead to real-world solutions for global challenges. Capacitors, essential components in electronic circuits, rely on Coulomb's law to store and release energy. By separating charges on two plates, capacitors create an electric field and store potential energy. The amount of energy stored depends on the force between the charges, which is determined by Coulomb's law. This principle is at the heart of many modern technologies, from smartphones to power grids. Electrostatic painting is a technique that uses Coulomb's law to apply paint evenly to surfaces. By charging paint particles and the object being painted with opposite charges, the paint is attracted to the surface, resulting in a smooth, even coat. This method is widely used in the automotive and manufacturing industries, showcasing another practical application of electric forces. Modern photocopiers and laser printers use the principles of Coulomb's law to transfer toner particles onto paper. By manipulating electric charges, these devices create precise images and text, demonstrating how fundamental physics can be harnessed for everyday technology. Even in biology, Coulomb's law plays a role. The interactions between charged molecules such as proteins and DNA are governed by electrostatic forces. These interactions are critical for the structure and function of cells, influencing everything from enzyme activity to cell signaling. The structure of DNA and proteins depends on the balance of electrostatic forces between charged atoms and molecules. Coulomb's law helps explain how these complex molecules fold and interact, which is essential for understanding genetics and biochemistry. The properties of many materials such as plastics and ceramics are influenced by electrostatic forces between their constituent particles. Coulomb's law provides the foundation for understanding these interactions, which is crucial for developing new materials with desired properties. In astronomy, Coulomb's law helps explain phenomena such as the behavior of plasma in stars and the interaction of charged particles in space. These forces play a role in the formation of stars, the dynamics of galaxies, and the behavior of cosmic rays, highlighting the law's universal relevance. While Coulomb's law deals with electric charges, it's closely related to the laws of magnetism. Moving charges create magnetic fields, and the interplay between electric and magnetic forces is described by the broader theory of electromagnetism. Understanding Coulomb's law is the first step toward mastering these more advanced concepts. Let's recap what we've learned. Coulomb's law describes the force between electric charges, providing a mathematical framework for understanding a wide range of phenomena. From atoms to galaxies, the law's influence is everywhere. Its applications span physics, chemistry, engineering, medicine, and beyond, making it one of the most important principles in science. Coulomb's law has stood the test of time, remaining a cornerstone of scientific understanding for over 2 centuries. Its simplicity and power have inspired generations of scientists and engineers, driving innovation and discovery. As we continue to explore the universe, Coulomb's law will remain a guiding principle, helping us unlock new mysteries and expand our knowledge. As we look to the future, the principles behind Coulomb's law will continue to shape science and technology. From developing new materials to advancing our understanding of the universe, the study of electric forces remains as relevant as ever. By mastering the basics of Coulomb's law, you're taking the first step toward a deeper appreciation of the physical world and its endless possibilities.